Welcome. In this video, we will look at departmental planning, how we group workstation, design layout, and analyze material flow. I'm Beliz. Let's get started. Departmental planning means grouping collection of workstation to optimize the facility layout. We combine workstation that perform similar functions, produce similar products, or use similar processes. The goal is smoother flow and lower cost. Departments fall into four categories: production planning departments, the core manufacturing areas, support planning departments, maintenance tools room, administrative planning departments, offices, HR, and service planning departments, cafeterias, medical rooms, and etc. Each affects that differently. We match layout type to product characteristics. For standardized products with large stable demand, use a production line or product layout. For physical large awkward low demand product, fixed material location like shipbuilding. For parts group into families with similar manufacturing needs, product family or group layout or cellular manufacturing. For all other cases, process department or job shop layout we use. Cellular manufacturing brings major benefits: reduced inventories, less space, fewer machine breakdowns, less rework, and lower cost. It also simplifies communication, material handling, and production scheduling, and it improves productivity, flexibility, and quality, and work satisfaction. How do we create these cells? Four main methods. We have four main methods: classification and coding, assigning costs to parts based on features; production flow analysis, following the root of parts; and the clustering technique like direct clustering algorithm and rank order clustering, and heuristic procedures or mathematical models we can use. Direct clustering is a simple step-by-step approach. First, order rows and columns by the number of ones. Second, sort columns. Third, sort rows. Fourth, form cells. Let's look at each step a little bit closer. Step 1, sum the ones each column and each row. Order rows by ascending number of ones. Order columns by ascending number of ones. This prepare the matrix. Step 2, sort the columns. Shift any column that has 1 in the first row to the left side, then move the second row, and so on. This starts the clustering ones together. Step 3, sort rows. Shift rows upward column by column to form blocks of ones. Finally, step 4, identify opportunities to form cells where all processing for each part occurs within a single cell. If some part needs machines from different blocks, you might need to move, machine, or split a part. In here, we are applying step 1, ordering them in descending order. Then we are shifting the columns that are intersection to the left side. Then we cluster them as 2 or 3. But you should note that both cell A and B require the use of machine 1 and machine 3. Ideally, the machines in a cell are not to be dedicated, so it's associated part family. However, this is not the case since machine 1 and machine 3 operates on the part families on cell A and cell B. These machines are commonly called bottleneck machines since they bind the two cells together. A common practice is either address the parts of particular part family that go to these machines or bottleneck machines themselves. The parts can be removed from the part family, redesigned to operate on other machines within its corresponding cell, or outsourced. Now, A rank order clustering algorithm. Another clustering method, it uses binary weights to group parts and machines. We have four steps: assign binary weights and calculate decimal weights for each row and column. Then rank elements in the ascending order of those decimal weights. Then repeat for columns, iterate until no further change that gives stable clusters. We are assigning binary weights for columns, and rightmost column gets the weight of 1. Next left gets 2, then 4, then 8, and so on. For rows, the bottom row gets again 1, moving upward, multiplying each cell's value 0 or 1 by its column weight, and sum across the row gets decimal row weights. Do similarly for columns. This matrix shows an example with 4 strategies and 6 learners. In here, we're ranking row by the scanning decimal weights. In example, row 1 has the weight of 57, row 3 has 41, row 2 has 18, and row 4 has 4. So the new row order is 1, 3, 2, and 4. Then we are repeating the weighting and ranking for the columns. After reordering rows, we compute column weight and reorder columns. Here the new column order becomes 1, 3, 6, 2, 5, and 4. Last step is iteration. Stop, reorder rows again based on the new column order, continue until the sequence stop changing. The final matrix shows clear blocks. Here row 1 and 3 form a one cluster, row 2 and 4 another one. That's stable grouping. Once we have departments, we need to measure flow between them. Flow is critical for arranging departments. For high volumes, we use quantitative measures, number of moves, distance. For qualitative needs, like communication between offices, we use closeness rating. Several factors affect flow: production volume and lot sizes, unit load size, and material handling system, the building's layout and shape, and activity relationship between machines and departments. Flows can be measured in pieces per hour or described qualitative as must be close. We have several graphical tools: the flow process chart, flow diagram, flow from to chart, a relationship chart, and relationship diagram. These help visualize the quantified and movement. Here is from to chart example. A company makes 3 components with different routing. Component 3 is twice as large, so we adjust flow units. The initial layout sequences A, B, C, D, E, but by rearranging so A, C, B, D, and E, we reduce backtracking. The from-to chart shows flow intensities between each pair. Our goal is to minimize total travel distance and could be backtracking as well. When quantitative data isn't available, we use relationship chart. It assigns closeness value. A is absolute necessary, E is especially important, I is important, O is ordinary closeness is okay, U is unimportant, X is undesirable. We determine these through interviews with managers and department staff. To create one, list all departments. Then for every pair, decide the relationship value and the reason code. For example, frequency of the user information flow, gather input from each department, and for management, discuss and refine until everyone agrees. This slide shows a real example. Departments like directors, conference rooms, president, sales, personnel, plant manager, and etc. Each pair gets a letter and a numeric reason code. That relationship chart then guides the layout, placing A's next to each other, X's far apart. That concludes our look at the departmental planning. We have covered layout types, clustering algorithms, flow measurement, and relationship charts. In the next video, we will put these into practice with detailed layout design. Thank you for watching.